Swayam Prabha. Digital India. Educated India.
Dear students, so far we have seen the three-phase sources where we have seen the star connected source. Just to have a look, you can see here, and the delta connection also. So we have seen in the case of delta connection, the line voltages and the phase voltages are same. So just to recall and write down that clearly, after that we'll be talking about the loads. So now we can just write this: three-phase AC supply which is balanced. Balance means the magnitude is same and the phase difference is also 120 degree. Okay, so in case of star connection, we have line voltage as root 3 times of phase voltages, and in delta connection we have line voltage as phase voltage. So this is one of the important thing. So now just to have an idea, the phase can be represented by this, which is basically a kind of coil or winding in general. So this is suppose phase A, and this is phase B, and this is the third phase, which is C. So this terminal where all the other terminal of the winding is connected of all the three phases, it is known as a neutral. So in a star, if we have a three-phase 4-wire system, then the line voltages of this with respect to neutral, so VA with respect to neutral is phase voltage. Similarly, we have other phase voltages as VBN and VCN. So these are basically the phase voltages. When we talk about the line voltages, then we have the line A and the B. So VAB is nothing but the line voltage. Okay, so VAB, VBC and VCA, these are the line voltages. But when we talk about the delta, then we have this kind of connection. Here you can see clearly phase A, B and C. So the phase voltage VAB is nothing but the line voltage between the terminal A and B. So phase and line voltage, so VAB, suppose this was, okay, so these are the VBC and VCA, where the line and phase voltages are same. This is what we have seen. So now, as I said, these either can be represented by these windings, or we can have another representation in few books where these phase voltages are represented as a different sources connected in this particular connections. So star or delta, you can have this kind of star where these are the AC sources. Okay, this can be VA, VB, VC, so something of this kind, and then delta also you can have the same kind of representation. So this is the about three-phase AC supply. Now let us consider the kinds of loads. So when we talk about the load, we will be talking about the balance load. So three-phase balanced load. So three-phase balanced load means the load which is being connected to the supply or the phases A, B or C in the three-phase system should be identical. It means that each phase should be loaded to the same kind of impedance. So for example, let us this time we'll be using this just to get familiar. So these are the three phase star connected supply, and this is phase A. Then we have some impedance, which is also star connected. Okay, so this is connected to this terminal, and then here. So this is line A, line B, and the line C. This is neutral, and we can have this as a some common point, like maybe some S. This is a junction. This Z, and Z. So Z is basically, so this is the magnitude and this is the phasor. So Z angle phi. So this is the impedance which is offered or connected to each of the load irrespective of the phases. So here this is neutral, then this is VAN, VBN, VCN. So these are the phase voltages. Now here we see that if we connect this neutral to this neutral, then there is a three phase 4 wired system, right? So in case of 3 phase 4 wired system, now let us consider what are the good things. So you can see, let me mark the phase A, which is the red color. So just I'm marking the closed loop which is being formed by these. So this is a phase A. Then we can have this, suppose phase B connection, right? So phase B goes, this is just to show you what are the closed path which we just see in the circuit. This is the phase B, and the remaining one which we can mark with the black color can be a phase C connection. Okay, this is your phase C. So there are 3 phases and 3 loops which are being shown: red, green, and black. So now if you see, what you can write is the phase current. What is the IA? IA is the current which is flowing in the phase A. IB is the current which is flowing in the phase B, and IC is the current which is flowing in the phase C. So IA is nothing but V phase A N, just clearly we write VAN by Z. So VAN is nothing but phase voltage, right? Z angle phi. So this is VP by Z or Z angle of minus phi. So this is the phase A current. Similarly, if you see phase B current is nothing but VBN by Z, and VBN nothing but phase voltages, and the angle will be minus 120 degree divided by Z angle phi. So this will come out as V phase by Z angle of minus 120 minus phi. Okay. Similarly, IC, if we solve it will be like VP by Z angle of minus 240 minus phi. So this is the line currents. Now if you see the phase current which is going in the phase of this winding, like the current which is flowing through this each phase is same. So in the star connection, phase current is equal to the line current. So here if you see, the current IAN is nothing but the IA. Similarly, IBN is nothing but the IB, and the ICN is nothing but the IC. So IAN is the current which is flowing here. IAN AN is I AN is the current which is flowing here, which is same as the phase current. So line current and phase currents are same. One of the interesting property or the calculation, if you see, if you add IA plus IB plus IC, and this is nothing but the IN, if you apply the KCL. So basically this is nothing but the KCL at node or point N or junction N, whatever you call. So this neutral, if you apply the KCL, you'll get this current, right? So, and if you calculate this, the IN will turn up as Vp by Z. If you take a common, 1 angle minus phi plus 1 angle minus 120 minus phi plus 1 angle minus 240 minus phi. This is from these values. So now this will be nothing but the 0. The phasor sum will be 0. You can just check it out by putting the value. So you can convert into sine or cos form and then find out that neutral current is 0. This is true only balanced load condition. So the neutral current will be 0 if the phases A, B, C currents are balanced. Balance means the magnitude is same, Vp by Z, and the angle is also having a phase difference of 120 degree. Now let us draw the phasor diagram of these three phase connected supply. So let us have the reference as the phase A voltage. So this is phase A voltage. This is phase B voltage. And this is phase C voltage. Phase A and B is having 120 degree. Phase B and C also difference of 120 degree, and this also 120 degree under the balance supply condition. Now if you see the current, this is phase voltages by Z. So consider this as a phase voltage. Now if you find out the current IA, this is IA, which is nothing but VA by Z, angle of minus phi. So you can see this angle is nothing but phi. Similarly, we'll be having a IB. This is phi, which is 120 minus phi in this direction. Then we'll be having a current of IC, and this angle also phi. So this is a phasor diagram. If you want to calculate the line voltages, then you can have a VAB, which is, so VA, VB and VC are the phase voltages. So line voltage is VAB, which is nothing but VA minus VB or VA plus of minus VB. So why I have written this in this particular sense? So this is nothing but the minus opposite to this. So this is minus VB, and now add these two. This is, so this vector is nothing but VA, and then VA and VB, if you add, you'll get VAB. So this is VAB, and this is 30 degree, and the VAB, this will turn out to be root 3 times of VA, which is root 3 times of phase voltages in terms of magnitude. Okay, and there will be an angle phasor difference of 30 degrees. So the line voltage will be leading the phase voltage by 30 degree in star connection. So this is how we have done earlier. Now for load also I have drawn the current. So now let us see for a delta connection balanced load. So quickly, if you'll see the delta connection of the loads, Okay, so if it is connected to some three phases, we'll assume as phase A, this is line A, line B and line C for time being. So the current which is going in this is IAB, in this IBC, and in this ICA. So if you see the current which is coming here as a IA, IB and IC, there is no fourth wire, there is no neutral point. So what will happen, the current will get divided here. Some portion of the current will go here, some portion current of this go here. Similarly, some portion will go here and some portion will go here of this IC current. So the net current IAB we have to formulate. So in this case you can see that the phase voltage and the line voltage are same, but the current which is flowing in the delta connected load we have to find out. So now let us see IAB. So the phase current, if I want to write IA, apply the KCL at this node, it is nothing but IAB. Okay, so let us, okay, we have marked the direction in the wrong way. So what we can do, we can have this current ICA in this direction just to have a symmetry, that's all. So IA is nothing but IAB minus ICA. This is from the KCL at point A. So this is suppose the point A or phase A which is coming at this point. If IA is getting divided, so IAB minus ICA, and if you write the phase current IB is nothing but the line voltage IB nothing but IBC minus I of AB, and the IC is nothing but ICA minus I of BC. Okay, so this is how we have drawn this current. Now if you solve this, solve in the sense, what is the current IAB? Okay, so now if you calculate the value of IAB, it is nothing but VAB by Z. VAB by Z. So VAB is nothing but V line voltage angle of 0 divided by Z, right? This is Z, this is Z, and this is Z, like balance load. So Z magnitude, this is Z phasor, and this Z magnitude angle phi. So this is VL by Z angle of minus phi. Similarly, IBC will be nothing but V line by Z angle of minus 120 minus phi, and ICA is nothing but VL by Z angle of minus 240 minus phi. So these are the values. Similarly, if you want to calculate the IL or IA, which is IAB minus ICA, okay, and apply the values from here, so that will come out to be root 3 times of the phase voltages, right? Magnitude wise. So in this case, the line current, which is IA, IB and IC, will be root 3 times of the phase current. So this is how the findings we can get when you substitute the values from here. So this is the magnitude, okay. So this we can see from the phasor diagram, so this will be clear. So now let us draw the reference voltage VAB as a so this is VAB, this is VBC, and this is VCA. So this is the phase voltage, which is equal to the line voltage, right? So this angle is 120 degree, this angle is 120 degree, and this angle is 120 degree. Now this is balanced voltage which is appearing across the load. So now if we want to calculate the IAB, so the phase current will be, here you can see the IAB, right? IAB is nothing but VAB by Z. So here you see VAB by Z. So this is IAB, and this angle is nothing but the phi. Similarly here, this angle is nothing but the phi. This is IBC, and this is nothing but the ICA, which is making an angle of phi here. Okay, now if you want to calculate the line current, which is IAB minus ICA, so for one I am trying to demonstrate here, so which is nothing but IAB plus of minus ICA. So ICA is this one, so minus of ICA will be here. Okay, and then you have to add this IB. So this is IAB, and this is minus I of CA. Now when you add, this is the current. This is nothing but I of A. Similarly, you can have the other values, phasors. Okay, so this is minus IBC, and if we add these two, you'll get I of C. Similarly, here also you are having this IB. Okay, so these are the phase and line current relationship where we can find out the values. Is it okay? So this is the balanced load which is connected for delta connection with the supply. So this is how we are going to be dealing with it. Now in case of unbalanced supply, the angles will change, but the philosophy will remain same. The angle phi will be different in case of unbalanced load, or the magnitude of Z per phase will be different, which means that the values which we are taking here, this Z will not be Z angle phi, this will be Z1 angle phi 1, Z2 angle phi 2, and Z3 angle phi 3. So that is the only difference. Rest all of the things will be same. So the per phase, like phase A, will be having an impedance of Z1 angle phi 1, for phase B Z2 angle phi 2, which is C, Z3 angle of phi 3. So this is the only difference, where phi is same here throughout. Per phase the value of phi 1 and the magnitude of Z1 will change. So that is the only difference in the balanced or unbalanced load. Okay, here we have seen the load and the source, their connections, and we have understood the phase and the line current connection, or the relationship between these parameters in case of star and delta connected system. Let us now consider one of the very important part, which is the measurement of three-phase power. So when we talk about the measurement part, okay, so this is very important topic, which is measurement of power. in case of three phase. So one of the very interesting part is that you can have a wattmeter. So let us first see what is a wattmeter, then we'll discuss further. So when we have wattmeter, we will connect the across the phase, we measure the voltage, and then we connect the coil in the series, which gives you the current, and we multiply the voltage and the current. This is the relationship between these voltage and the current for calculation of the power. Now if we consider the wattmeter, suppose there are two wires, there is some live conductor or this some phase A, and this is a neutral. Okay, so when we try to connect the wattmeter, what we'll do, in the series we'll connect one coil. It will give you the measurement of current, how much current is flowing through this phase, and then we have a resistance which is connected to this neutral. So this is neutral, this is line wire A, and this is the representation of the wattmeter. So this is the how the wattmeter represented. So we are not going into the internal design and other things, but we know how to connect this wattmeter across the phases to get the power done. So this is wattmeter. So now what we are going to do, we'll see the case of three phase supplies, right? So we have this is source, three phase. We are not bothering what kind of source we have. It can be a delta connected or star connected. Now let us see, this is phase 1 A, phase B, and the phase C. So this sub source is giving three phases A, B, and C. And if this is a, okay, let us consider three phase 4-wire system. When the neutral is connected, so now one more connection comes, which is neutral. So when you have a wattmeter, you can connect like this between phase A and neutral. So you should have a this will give a rating 1. So the wattmeter will show you some P1, or we can write as PA. And if this is a balance supply, here we can connect the same connection with phase B. Okay, so now we have phase B and the phase C. So one by one we'll connect between these phases and neutral. Then we'll get three readings, PA, PB, and PC. So if this is a balance condition, this will be nothing but PA will be equal to PB equal to PC, which means that in balance condition, 1 wattmeter reading can be multiplied by 3. 1 wattmeter is sufficient to measure the power, which is nothing but 3 PA. Okay, this is three phase power. Okay, this is very simple. So this is 1 wattmeter connection when you have a neutral available with you. So this is the only method where you need to have a neutral for a connection. So suppose the neutral is not available. Okay, so first we'll see what if neutral is not available. So three phase power supply, no neutral. Okay, three phase 3-wire system. So when we have three phase 3-wire system, so we have phase A which is coming from somewhere, then we have phase B, okay, so which is coming from somewhere, and then we have phase C. So let us draw this phase B little down, phase B. Now when we try to connect the wattmeter and measuring the reading with only 1 wattmeter for 3 phases, we will be connecting one coil here. Now where to connect this? This should go to the neutral, but there is no neutral. So what happens? We load the system with a very high resistance, and we create artificial, or so this is N prime. This is artificial, or we can say temporary connected neutral. Okay, so this is artificial neutral, and this is your wattmeter. So normally this is represented in circle. So this is how we create a artificial neutral with a resistance R and measure the values. So now if you reverse this, reverse means now you can connect this coil in phase B. Okay, so and this is connected to some neutral where one is connected here and one is connected to phase A. So this will show you the phase B, A and C, and similarly you can have A, B, and you can have wattmeter connected in series. So normally this is the idea of having an artificial neutral. So one resistance here and this is the another resistance R, and this is your wattmeter. This is wattmeter and this is wattmeter. So these are the ways by which we can have a power which is the meter will show P1 or PA, PB and PC, and the sum of these three power will be nothing but your three-phase power. So this is the idea of measuring the power using one wattmeter. Now one of the very interesting method is 2 wattmeter method. So how can you measure a three-phase power at once just by connecting 2 wattmeter? Okay, so let us first understand the power is nothing but VA IA plus VB IB plus VC IC. Okay, this is corresponding to each line A, B and C, and we have seen that balance cased IA plus IB plus IC is nothing but 0. So in this term we can write IC as minus IA minus IB and then substitute this value here. So now substitute these values in the above expression. So the power will be nothing but VA IA, which is phase A, plus VB IB phase B, plus VC, and IC will be nothing but IA minus IB. So if you just write this, to VA minus VC times of IA plus VB minus VC times of IB. So it clearly indicates that this is the reference voltage and these are the currents. So you need, for measurement, we need 2 currents, IA and IB, and voltages VA and VB with reference to C voltage, VC. Okay, so now VA with respect to VC will be VA minus VC. So how the connection will look like? So just look at the connection. So now you have phase A, okay, and then you have phase B, or you have phase, so you write phase A, phase C and phase B, just a representation. So what will happen, you will be connecting the wattmeter in phase A and phase B so that you can measure the current of these lines. We'll be having phase A current measured, and then we have phase B. So this is the, so this gives the voltage with respect to C, and similarly this gives the voltage. So this is how the wattmeter is connected. wattmeter 1, W1 and W2. So W1, W2 will give you some reading PA or PB or P1, P2. So the three-phase power is nothing but the sum of W1 reading plus W2 readings. Whatever the wattmeter shows, this is the sum of these two. And using the only two wattmeters, we can have a three-phase power calculation only with the reference when we connect this connection. So the connection of the wattmeter is important in this case. So it can be connected to phase A and phase C with reference to phase B also. So any two phases will be used for a wattmeter current measurement with reference to the voltage of the third phase. That's the idea of two wattmeter method. So if you have a three-phase 4-wire system, you can connect 3 wattmeter with reference to the neutral. It will be the same philosophy, and then you can measure the power. So now let us see the mathematics of the power the values, which is nothing but, if you consider volt amperes, which is your complex power, then your real power and reactive volt amperes. Okay, so we know that if you have a single phase circuit, so S in single phase is nothing but V and I, the product of these two, which is your volt amperes, and you have a phase of phi, so S. So if you remember, S single phase can be written as P plus JQ, and P is nothing but the real component and Q is the volt ampere. So real power plus reactive power is equal to the complex or apparent power. Now in case of a three phase, it can be either by 3 times of single phase measurement, which is nothing but 3 times of V phase and I phase, simply, right? So this is the idea which we have taken. So if each phase and the current, if you are known, you can just calculate the phases per power per phases and then just sum up them. Now in a case of RMS values, so these are the RMS values. Anyway, we'll be considering the RMS values. So V phase is nothing but V line by root 3 in case of star connection, and I phase is nothing but I of L. So for star connection, okay, so S, the complex power in three phase, is nothing but 3 times of VL by root 3 into IL, so it will be root 3 VL IL, or 3 times of V phase I phase. This is S3 phi, or three phase power, right? So this is the idea. This is volt amperes. Similarly, for delta connection, three phase will be 3 V phase into I phase, but in delta connection we know that V phase is equal to line phase, but the line current is root 3 times of phase current. So here we can write it as 3 VL IL by root 3. So we have root 3 VL into IL. This is S of three phase. So in both the cases means the star and the delta connection, the power is nothing but root 3 times of line voltage and phase voltages. So here if we write it clearly, so S three phase in all the cases will be root 3 times of VL into IL. So in three phase case, so if we represent the real power, which is nothing but root 3 VL IL cos of phi, and Q of three phase will be nothing but root 3 VL IL sin of phi, where phi is nothing but phase angle of voltage and the current balance. Then it will be same for all the phases. Okay, so this is the idea of calculating the power in a three-phase system. So with that, we will be closing this our three-phase circuits. We'll be solving some of the example and the power measurement of three-phase supply. So with that, we'll be closing this lecture. So next time we'll be seeing one or two examples which will be solved using these methods.